Hello guys, welcome to module number 12 of machine learning and artificial intelligence. So we're going to look at four subsections, and subsection 1 we're going to look at deep learning with TensorFlow and PyTorch. We are going to look at subsection 2, which will entail natural language processing or NLP as a shorthand. And number 3, we're going to look at reinforcement learning. And finally, we're going to look at computer vision with OpenCV. So all explanation will be made in the pragmatic section. So stay along with us as we head in that section. So, Module 12, Advanced Machine Learning and Artificial Intelligence. So this comprehensive module covers deep learning with TensorFlow and PyTorch, natural language processing, that's NLP. Also look at reinforcement learning and computer vision with OpenCV library. And each section will include theoretical foundations, practical implementation, and real-world application examples. And in this section, we want to look at deep learning framework. So deep learning involves neural networks with multiple layers that can learn complex patterns from data. And we have two dominant frameworks that are TensorFlow, that was built by Google, and PyTorch, which was developed by Facebook. And it's time to start with TensorFlow. So before we do it, we need to install using pip install TensorFlow and hit enter. So let us have an example in TensorFlow. So we need to import TensorFlow as TF. So we need to import TensorFlow library for building and training models. And we need to import NumPy as NP. So import NumPy for numerical operations. As well, you need to import matplotlib.pyplot as PLT, and so for plotting graphs. And let us define our load and preprocess data function. So we need to load and preprocess MNIST dataset, which entails inbuilt dataset for images. So load MNIST data, and we need to return the training and test set. So x underscore train, y underscore train, comma, x underscore test, y underscore test is equal to tf dot keras dot datasets dot MNIST dot load underscore data function. And we need to normalize the pixel values to the binary by dividing by 255. So x train is equal to x underscore train dot as type plot 32 divided by 255.0. X underscore test is equal to x underscore test dot as type plot 32 and divided by 255.0. And now it's time to reshape the images from 28 by 28 pixels to 784 dimensional vectors. This means they will be flattened images. And x underscore train is equals to x underscore train dot reshape -1 to 784. X underscore test will be x underscore test dot reshape with -1 and 784. And we need now to return the x underscore train y underscore train x underscore test y underscore test, which will return the preprocessed MNIST dataset. And now let us define our model. So we need to build our model function. So we need to build and compile the neural network model. Now model will be tf.keras.sequential, and simply we are just creating a sequential model which is linear stack of layers. And so tf.keras.layers.length will be 128, and activation layer will be relu, and the input shape will be 784. This will be the first hidden layer with relu activation, and input shape will be 784. So again, tip.keras.layers.length 64, activation layer will be relu again, and this will be the second hidden layer with relu activation as well. And tf.keras.layers.length will be 10, and activation layer this time will be softmax, and so this means that output layer with softmax and activation function for 10 classes. And now moving forward, we want now to combine the model with Adam optimizer, sparse, categorical, cross entropy, loss, and accuracy matrix. So our model dot combine will take parameters optimizer, which will be Adam, and this will be just an optimizer that we are going to use in this case. And loss function will be sparse underscore categorical underscore cross entropy. This will be the loss function for multi-class classification. And again, you can have a matrix as with accuracy. This will be the matrix to track during the training, and we can proceed by returning the model, which means we want to return the compiled model. Now we want to define or to create our training model function with model x underscore train, y underscore train, x underscore test, and y underscore test. So we simply training the model, and we want to plot the result as well. So let us add some early stopping to prevent overfitting by monitoring validation loss. So early stopping, which is our object, is equals to tf.keras.callbacks.early stopping. This we can say with parameters like monitor will be valid loss, and this will monitor the validation loss during training, and patient will be 3, which will stop the training if no improvement is recorded after 3 epochs. And we need to restore underscore base weight, which will be true, which means that we need to restore the weights from the base epoch. And we can train now the model on the training data and validate on test data. So let us have our history to be model.fit, and this one will take x train, y train as parameters with which index training data and labels, and validation underscore data will take x test and y test, which means that these are with the validation data and labels respectively. And now our epoch will be 20. So we will have from epoch number 1 up to epoch number 20, which will be simply the number of epochs to train, and batch size is going to be 64. Then our callbacks will be we take the function, we take the parameter of early stopping, which we used early. We used early as we had defined before, and the verbose will be 1, which means that we need to display the progress during the training. And again, we need to plot the training history, that is accuracy and loss. And so plt.figure and we pass on the figure size as 12 and 4. So we're just setting the layout of our graph. So and we also want to have some subplots, like plt.subplot 1 to 1, and want to create subplot for accuracy, and we also need to do what now, to plot the history with accuracy, and label will be training accuracy. So this will be the plot for training accuracy, and plt.plot history with val accuracy, and label will be validation accuracy. Yes. And plt.title, the title of our title of our plot will be accuracy over epochs. And plt.x label will be epoch. This which means our x-axis will be labeled as epoch, and also need to label our y-axis as accuracy. Again, you can also add some legend to our plot. And now we can also again add another subplot to create a subplot for loss function. So plt.plot, we need to plot the history for loss function with label training loss, and we need now again to plot the training loss. Now plt.plot history with validation loss, and label will be called validation loss. So this simply upload to validate the loss. And now we can also add some label as epoch on x-axis, and y label again as loss. Jamaa tukutuku vipi? Hapana bado. And again now we want to plt.tight layout, so which means to adjust our layout to prevent overlap. Then plt.savefig, so we want to save our image to our working directory. And plt.show, one now to again to display the image. Despite saving, we also want to display it. So we want to return again the model. That's the trained model. Again, let us now define our model evaluation function with model x-test and y-test. And this one will evaluate the model performance. So test underscore loss, test underscore accuracy will be model dot evaluate x underscore test y underscore test with verbose 0, which means we just want to evaluate the model on test data. And now we can print the test accuracy as test arc in 4 decimal places. And as well, you can print the test loss to be the test underscore loss as well in 4 decimal places. Now we want to show some example prediction, and predictions will be model.predict x underscore test, so which means the first 5. We want to get the prediction for the first 5 test samples, and we can now create our predicted labels object as np.argmax, and person prediction and axis is equal to 1. So we want to get the predicted class labels. And now we can also do plt.figure, which we just want to create a new figure for prediction, and it will say that we can use for loop for I in range 5. So we want to look through the first 5 test images, and we need now to plot our subplot. This means we want to create a subplot for each image that will be produced, and plt dot im show or image show x test dot reshape 828 by 28 map will be gray, so we want to display the image and it will be in grayscale, and plt dot title will be predicted underscore labels and will be true. So we want to set the labels to be true. So and now we just want to display the predicted and the true labels or true labels, and plt.x-axis we can put it off or we can hide off, and the plt.tight layout, which means we want to adjust layout to prevent an overlap, and plt.savefig, which we want to which will be sample prediction.png. So we're saving the plot as an image file to our working directory, and plt.show we want now to display again the same plot. And now we can now define our MNIST example. So we want to load and pre-process the MNIST image dataset. So x underscore train, y underscore train, comma x underscore test, y underscore test will be equal to load underscore and pre-process underscore data function. So next step is to build the neural network model. So model will be equal to build underscore model function, and now the following follows. We want to print the model summary, that's the architecture and the number of parameters that will be produced. Let us have a print function model summary, and will be model dot summary, and we want to train the model on MNIST dataset. Now we want to print, for example, training model on MNIST data dot and model is equals to training underscore model with model x train, y train, and x test, y test as parameters. And then the next step is to evaluate now the trained model on the test data, and now evaluate underscore model will take model x test and y test as parameters. Now let us finalize with if underscore name underscore is equal to underscore main underscore full colon, then it means that we want to suppress the TensorFlow information messages, which means that which are set log level to only show errors. We need to import OS, we need to import OS, and then OS.environment we need to pass on this function, and which will be equal to 1, and 0 will mean that all messages, 1 it means that no information, 2 it means that no warning, and 3 will mean that no errors. So in this case we use to 1, and we need now to run a MNIST example to see the result. So in VS Code I can run py ml ai.py, and if I hit enter, I know this will take some time because a lot of stuff's happening under the hood, so it takes some patience to wait for the result. So it's still processing the result because we have like 1 up to 20 epochs that we need to get the result from. And don't worry, because everything will be explained in a clear manner. So let us give it a time, some time as it processes. Yes, the first table has been produced. Can you see this fancy table with some summary statistics here? This is sequential model sequential with it has 3 layers, then underscore 1, then underscore 2 with some summary here. You see the total parameters were 109,386, and you can see the memory allocation that used to generate this, and also trainable params were the same exact number 109,386, which means that no parameter was skipped during the training state. And you can check also that none trainable parameters were 0. So which means every parameters here were trained. So let me move a little bit here. So you can see this epoch number 1 has successfully loaded, epoch number 2 of 20 are also successfully loaded, and other epochs are still loading. So let us give it some time as it continues to load this one. And remember, it will depend the internet speed from your side. Now we are on epoch number 10 of 20. Again, you need to continue to observe what's happening. You have the accuracy level for each epoch. For example, epoch number 10, it has an accuracy value of 0.9951, which means approximate 99.51% with a loss value of 0.0151. And epoch number 1, for example, it had a value accuracy level of 85%, and from 85, can you see the next epoch is 96%, and the next 97%, the next is 98%. So you realize that it's increasing as we proceed. So it means that if you add more epochs, there's likelihood that you're going to get 100% accuracy. So we have some graph that has been generated after epoch 10 was reached. So let me show you the graph before we proceed. So these are the fun graphs that you can see. You have two subplots here. So we saw creating some subplot functions. These are the subplots that were generated. So the first subplot is here with accuracy over epochs, and the blue line here showing the training accuracy, while this orange one showing validation accuracy. And if you can proceed on this graph on my right hand side, you find that the blue one is a training loss, while the orange one is a validation loss. So don't worry, because these things we're going to be explained in the following section. And now we have our overall. Before you head to overall, we have this graph that has been generated. So this is an image. So remember, I told you that MNIST dataset is an inbuilt dataset that contains labeled images. So and this image has been gone through training and testing, and now this is the final output. Can you see the all the training accuracy that was obtained was 100% sure, because you can see the predicted images or the labeled images are 7 were 7, and it returns true to bit 7. So there was no confusion that we trained the 7 images labeled as 7, and then at some point the model confuses 7 and 1, for example. So it predicted 7 of them and it returned them as true to be 7. So which means 100% accuracy. The same way too, those images that were labeled 2, 2 of them were predicted and 2 of them became true. The same one to 1, the images that were labeled 1, only 1 was predicted and the outcome was 1. And 0, labeled 0 was 0 and also came as 0. And finally, the one that was labeled 4, the same, and output was still 4. Now you see how machine learning is doing amazing stuff. It's making data analysis to be interesting. So let me close and we check now our final accuracy. So remember that our final accuracy is about 98%. So it's 0.9776 with a test loss of 0.0745. This is amazing. So the next stage is we're moving to discussing our interpretation of our results, and of which I have given you some gist. So I hope you are going to connect the dots. we want to discuss and interpret what has just happened. So in the discussion and interpretation of the result. So number one, we want to look at the model architecture. So the model consists of 3 layers. So you can pause the video and check what I'm saying if they rhyme with yours. And the first dense layer had 128 units with ReLU activation function, resulting in 100,488 parameters. And the second dense layer had 64 units with ReLU activation function, resulting in 8,256 parameters. And output layer had 10 units with softmax activation, resulting in 650 parameters. And the total parameters were 109,386, which is relatively small, allowing for a quick training process. And number two is that the training process entailed or were epoch-wise, and the training process was carried out for 20 epochs as we've seen, and here are the notable results for the first few epochs. Maybe you can look up to number 11. So epoch number 1, the accuracy was 86.00% and loss of 0.426. Validation accuracy was 95.88% and validation loss was 0.1346. And at this point, the model already showed high accuracy and low loss on the validation set. And epoch number 2, the accuracy was 96.40% with a loss of 0.1190 and validation accuracy was 97.12%, and validation loss was 0.0893, and the model further improved its performance in both training and validation. And epoch number 3 is that the accuracy was 97.69%, loss of 0.0761, validation accuracy was 97.37%. So validation loss again was 0.0834, and this means that there was continued improvement in accuracy with a slight dip in validation accuracy, but still very high. And epoch number 5 had the accuracy of 98.71%. You can see the increment with a loss of 0.426, and validation accuracy was 97.43% with the validation loss of 0.0799, and further improvements with validation loss maintaining some stability. And epoch number 10 had an accuracy of 99.49% with a loss of 0.167, and validation accuracy 97.44%. The validation loss was 0.0948. So this very high training accuracy achieved. However, validation accuracy shows a slight plateau. And epoch number 11, the accuracy was 99.55%, loss of 0.144, and validation accuracy of 97.78% with a validation loss of 0.0924. And the model's accuracy approaches its peak, though the validation accuracy and the loss remain quite stable. And number 3, now we can look at the final test result. So after completing the training process, the model was evaluated on the test set, and the test accuracy was 97.90 as we saw in the VS Code, and the test loss was 0.784, and these results are indicative of a well generalized model demonstrating good accuracy on unseen data. So this is the summary of the key observations: that the model achieved high accuracy, starting at 86% and improving to nearly 99.5% by the end of training, that is at epoch number 20. And the training loss decreased over the epochs, which is a sign of effective learning. So the validation accuracy shows a minor fluctuation but stabilizes at around 97 to 98%, indicating that the model generalizes well without overfitting. And the final test accuracy of 97.90 shows that the model performs well on new and seen data. And we're looking at validation and test losses. We say that validation loss and test loss are relatively low, indicating that the model is learning without significant overfitting or underfitting. And statistical significance is that the training and validation accuracy consistently increased over epochs from epoch number 1 to up to 20, suggesting that the model is effectively learning the patterns from the menaced dataset. And the gap between training accuracy and the validation accuracy was minimal, implying that the model is generalizing well as opposed to overfitting the training data. And the validation loss remained fairly stable after the early epochs, confirming that the model is not suffering from significant overfitting. And now this interpretation suggests that the model is performing well, and further optimization such as tweaking the architecture or adjusting hyperparameters could improve the performance slightly. However, it is good to know that it seems to have already reached a high level of accuracy, which is suitable for most practical purposes. Now guys, it's time to look at PyTorch, and the first step is installation. We need to use pip install PyTorch or pip install torch and torch vision. So we use to define our PyTorch example function with import torch, which is a PyTorch based library, and also need to import torch.nn as nn for neural network components. Again, we need to import torch.optim as optim, and this is for optimization algorithms. And from torch vision, we need to import datasets. Again, transforms for loading and transforming again the minist dataset we've just used before in the previous model. And from torch.utility.data we need to import data loader for batch loading of data, and we need to import matplotlib.pyplot as PLT, which will be used for plotting purposes. We need to also import NumPy as NP for numerical operations. And again, we need to define a symbol feed forward neural network. So class neural net with nn.model or module, and we need to define using underscore init method with self parameter, and super neural net with self dot init method with self.fc1 will be nn.linear with 784 and 64 parameters, which means which will be the first hidden layer. And you can also have self.fc2, which will be nn.linear with 64 by 64, which is the second, again, hidden layer. And now you can define our third layer, which is self.cf3, which is nn.linear 64 by 10. This is the output layer with 10 classes. And self.relu, which will be nn.relu function. That's a relu activation function. And again, you can define the forward function with self and x parameter. So x, the first x will be self.relu with self.fc1 and x function. So we apply the first layer and relu. And the second is to apply the second layer, which will be self.relu and self.fc2 x, which is applying the second layer. And finally, we want to apply the third layer of our 10 classes. So x is equal to self.fc3, and that is it for output layer. That's logist or logits, and we can return now the value of x. And the next is to set the device. So we can use GPU if it's available. For my case, I'm using CPU. So my program will run on CPU by default. So device will be torch.device. So it will automatically choose CUDA if torch.CUDA is available. Else you can use CPU. Now you want to transform or to convert the images to tensors or arrays and flatten them in the long run. So transform will be equal to transforms.compose, which will take the values of transforms.to tensor function, which means we are converting images to tensor. So remember, tensor is just like an array, and transform.lambda, you can use the lambda function of x to x.view -1, which means we are flattening an 28 by 28 image to 784 vector. Now you can load the training and the test dataset. So train underscore dataset is equal to dataset dot minist, and the root will be our root working directory, where we want to use the same dataset. And train will be true, download will be true, you can transform, we say transform. And test underscore dataset will be dataset.minist. Route will be again the same working directory, and now this time we're going not to print them, and we are going to make the download to be true, and transform again to take on the transform. Now we can create the data loaders. We want to train underscore loader is equal to data loader with the function train underscore dataset batch underscore size is equal to 64, and you can shuffle is equal to true. And now you can also have test loader with a data loader and test underscore dataset batch size is 64 and shuffle is equal to false. Now you can initialize the model from a loss function and also an optimizer. So model will be neural net function to device, And also criterion will be nn dot cross entropy loss function. So for match class classification, and the optimizer will be sorry, optim dot adam with model dot parameters, and RA will be 0.00. So we're just using an Adam model, and we're training the loop now. Number of epochs this time we're going to be 5, as opposed to previous model where we used 20. And train loss will be an empty list, so we want to add it. For epoch in range, number of epochs that's 5. Model the train, so function. So we set the model to training mode, and running underscore load loss will be 0.00. So by default it will be 0. And for images labels in train loader, we want to do what? To have images labels be equal to images dot to device comma labels to dot to device respectively. And again, let us create our optimizer dot 0 underscore grad function to reset the gradients, and the outputs will be the model dot and you take on the images at arguments, which will be pass, which will be the forward pass, and loss will be the criterion with outputs and labels. So this one will compute the loss outputs. So the loss dot backward would be back propagation, and optimizer dot step function will be update weight load. And we can read now, we define our running loss as an increment of loss dot item function. So an average loss will be running underscore loss divided by length of the trained loader, and the train underscore losses dot append. You can append the average loss now, and you can now print the epoch, because in the epoch we meant by 1, and we divide by the number of epochs, and we say that loss will be the average loss into 4 significant figures or 4 decimal places. And you can evaluate now a model dot eval function, which means you set the model to evaluation mode, and now the correction to be 0, and the total again to be 0 by initial. So we can use with context manager. So with torch dot num underscore gradient, so we need to disable the gradient calculation for evaluation. And for images labeled in test underscore loader, so we need images and labels to take on the images dot to device comma labels dot to device again, and the output this time to be model with images, and underscore comma predicted will be torch to dot max with output dot data comma 1, and total will be an increment will be added to labels dot size, and you can correct also can be added to predicted, which will be equal to labels dot sum dot items function. And you can now print the test accuracy as 100 times the correct value times the total value in 2 decimal places. And so we want to show some example prediction. So example is equal to, we want to enumerate the test loader, and the batch underscore idx will be comma example underscore data example underscore target, it will be equal to next examples function, and example underscore data will be example underscore data dot to and the person the device, and with torch dot number underscore gradient will take on the output will be model and also the example data, and again underscore comma phrase will be torch dot max output comma 1, and example of data will be examples underscore data dot cpu dot num function, and the preds or predicted to be preds.cpu.numpty function, and you can also set the figure size of our expected plot. And now you just follow for I in range 5. We can have our subplot with this arrangement, and you can also show the image as example with the example data with some reshaped value of 228 by 28 and CMAP will be gray, and PLT.title will be predicted or pred, and will pass on each value, and PLT.axis you can put it off. So PLT.title layout follows with PLT.save figure, which means we want to save our final image to our working directory or anywhere that we prefer. So on PLT.show image, so we want to show again the image after saving. Now let us finalize our stuff by using our function underscore if underscore name is equals to if underscore. Okay, great. Let us move to key differences from TensorFlow. From this, what we've just learned, the difference from TensorFlow is that it is more Pythonic, object-oriented, and it's dynamically computed, or it has dynamic computation graph, and it has explicit forward pass definition. So it is time now to run our codes and find out what happens. Let me expand my terminal and observe what's happening. Remember, I just prefer using Notepad to write my codes because it gives me a wider interface to write the codes, but still the same way to just simply run it using also VS Code. So this stuff taking some significant time, so we have to wait, and I'll show you once it has completed. So you can check the epoch number 1 of 5, the loss function as 0.3905. So let us wait for the next epoch values and accuracy levels as well. Epoch number 2 and the loss value of 0.1777. Now finally we have epoch number 5 of 5 with an error with a loss of 0.0809. We realize that the loss reduces as the number of epochs increases. So, and the test accuracy of 96, and the test accuracy of this, the test accuracy 96.90, and the final loss value of 0.0809. Remember, we started at 0.3905. It has been reducing after each and every epoch, or after each and every training set. So we realize that after each and every epoch, the loss is reducing while the test accuracy is increasing, to be precise. So let me show you the graphical image. So again, the same prediction holds from what we did on TensorFlow. So we realize the same result we got on TensorFlow are the same result we're getting on PyTorch. So if we didn't get what we did on TensorFlow, slow down your video and get back some few steps and get what I'm saying. Everything that we got here, all our predictions are just similar to what we did on TensorFlow. Welcome again, guys. On section number 2, we're going to look at natural language processing, that is NLP. And you need to remember that natural language processing, or NLP, enables machines to understand, interpret, and generate human language in a way that is both meaningful and useful. It is a critical subfield of artificial intelligence, that is AI, that bridges the gap between human communication and computer understanding, allowing systems to process vast amounts of natural languages or natural language data effectively. And common applications of NLP or natural language processes include text classification, in which entails automatically categorizing text into predefined labels or topics, and this is widely used in spam detection, news categorization, and organizing customer feedback. Number 2 is sentiment analysis, that is determining the emotional tone behavior or behind a series of words to understand the attitudes, opinions, and emotions expressed in a text. So businesses often use this to analyze customer reviews, social media mentions, and survey responses. And number 3, next is machine translation, and it entails translating text or speech from one language to another. And the popular services like Google Translate use NLP to provide real-time translations that preserve the context and intent of the original message. So other noteworthy applications include chatbots and virtual assistants like Siri and Alexa. So speech recognition, text summarization, question answering, and information extraction from unstructured data. And let us look at text pre-processing using NLP. First of all is to install using pip install NTK space or natural language toolkit space, and the following are the imports. We need to import SSL, which is a secure socket layer that supports secure connections. Also need to import a natural language toolkit or natural language, yes, it's natural language toolkit for shorthand for text processing. Now from nltk.tokenize, we need to import word tokenize, and this word tokenize is used to split text into words. And from nltk.corpus, we need to import stop words. These are just common words like there, is, among others, to filter out. And from nltk.stem, we need to import Porter Tema. This is a tool for reducing words to their stem. And now from sklearn.featureextraction.text, we need to import tf vectorizer, which will convert the text from numerical form. And from sklearn.naive_bayes, we need to import multinomial NB, that is naive Bayes classifier for the text data. And now from sklearn.pipeline, we need to import make pipeline, and this is convenient way to chain pre-processing and modeling. Now SSL context fixed only for restricted environment follows. Let us have some sample or example. Try underscore create a unverified HTTPS context to be SSL dot create unverified context. Hence we need to try to bypass SSL verification. So SSL dot underscore create underscore default underscore HTTPS underscore context will be underscore create underscore unverified underscore HTTPS underscore context. This one will override the default context except attribute error. So we need also to pass. So we do nothing if the system doesn't support this override. And now let us set up the NLTK resources. We need to define a setup NLTK function or method to ensure the necessary NLTK resources are available. And resources is equals to pancake to tokenizers slash pancake comma stopwords Kupora slash stopwords. So these are required resources so far and path. So you can use for loop for res path in resources dot items function. We need to try and catch some errors if possible. NTK dot data dot find path. So we need to check if the resource exists, and okay, if the resource exists locally, except we need to look to return the lookup error. We need to print downloading missing NTK resources and pass on the resource itself, and NTK dot download res. So which means we want to download the resource if not found in the local working directory. And now let us look at our processing example. So this is pre-processing, sorry. So we want to define the demonstrate underscore pre-processing function, and now we want to just demonstrate a pre-processing colon tokenization, stopword removal, steaming, among others. So let us set up NLTK function to ensure the required NLTK data is available. So sample, let us have a sample intended to pre-process the text. So text is equal to natural language processing makes computers understand human language. That's an example of text. You can use words. Tokenization, or simply to how to convert, want to convert to lower and split into words. And let us have our tokens as word underscore tokenized text dot lower. And you can print tokenization as print the tokens. So let us have stop words removed, or I want to remove stop words. So we want to keep only meaningful words and ignore stop words and punctuation marks. So stop words will be set stop words dot words English. So we want to the filtered underscore tokens will be word for word in tokens if word is alphanumeric is alpha and word not in stop underscore words. We need to print after stop word removal, then we need to print filtered underscore tokens. So again, let us look at stemming. This is a way to reduce words to their base or root form. So stemmer is equal to quarter stemmer function, and stemmed tokens will be equal to stemmer dot stem and person the word, and for word filtered tokens, then you need to print after stemming, then you can also print the now stemmed tokens. So again, we now want to return the stemmed tokens. And also I will run this function together. I will see the output. So let us do classification example. We want to define the demonstration underscore classification example. So it will train and demonstrate a basic sentiment classifier using TF IDF plus naive Bayes, and the sample training data with labels 1, which will be positive, 0 will be negative. Let us have some text here as I love machine learning, and on the other hand, you can have deep learning is fascinating. Another sentence can be I hate bugs in my code. So the last, and debugging takes too much time. So remember the last two statements, and so okay, fixing errors is annoying. The last three statements, I can say the last four statements that I'm typing here, most of them are negative. So this tool makes my life easier. That is a positive statement. Coding is really fun. That is a positive statement. Solving problems is enjoyable. That's a positive statement. And nothing works. I'm frustrated. That's a negative as well. So you can have our labels as 1 1 0 0 0 0 1 1 1 0, and this one will the corresponding sentiments or labels of what we've just created. And we can create a pipeline that first vectorizes text using TF IDF, then applies naive Bayes. So we need to have a model object as make underscore pipeline TF IDF vectorizer function, comma multinomial NB function, and we have model.fit text labels, and then we train the model on the sample data. So the new text to classify will follow. The new text will be I love coding and debugging is so hard. So these are the tests that we're going to test. And prediction will be model.predict new text underscore text, and we want to predict the sentiment from the new text. So we need to display the classification result. So we need to print classification result colon, then for text comma label in zip text, new text, new underscore text, and prediction. Then we need the sentiment object to take on the positive, and that is if label is equal to 1, else if label will be negative. And we can use the negative icon and positive icon as well, and you can print the exact text of the sentiment. And now you can close our program, and if underscore name underscore is equal to underscore main underscore, then you can print an NLP demonstration script, and we print that text pre-processing, and you can try to catch some error, and demonstrates underscore pre-processing function. So we need to run the pre-processing demo exception as E. So we need to show the error back to the user or the person coding. So if the error occurs, we need to guide the user to install the required package, which will be NLTK tool. So print pre-processing error, and we provide the exact error. Print try running manually, import NLTK, and NLTK.download pan pt ltk.download stopwords, and now we can print text classification. Try again, we need to catch some errors. Demonstrate underscore classification function, and we want to run the classification demo except as exception as e. So, and which means if the error occurs, then we want again to guide the user to install scikit-learn package. So print classification error as e, and you want to print make sure the scikit-learn is installed. And now we say pip install scikit-learn. So the next step is to train and now predict. Now remember, before running a model, we need to do some, remember, in machine learning or ML, training, testing, and predicting are core steps in building models that can generalize well to new data. Now, let's have a look why each step is important. Number one is that training. So the purpose of training is to teach the model how to recognize patterns and relationships in the data and why it matters. So during training, the model learns from labeled data, that is input and output pairs, and it adjusts internal parameters like weights in neural networks to minimize the differences between predicted and the actual values. The quality and quantity of training data directly influences our model performance. And number two is that testing. We can look at testing. The purpose of testing, we've looked at training. Now the purpose of testing is to evaluate how well the model performs on unseen data. So training, we are training on seen data, and testing, we are testing on unseen data. And why does it matter? Testing uses a separate data set that the model hasn't seen before to assess accuracy, precision, recall, among others, and it helps detect issues like overfitting, that is when the model performs well on training data but poorly on new data or test data, and this ensures the model can generalize rather than just memory is predicting. So after testing, we need to predict. Now purpose is to apply the trained model to real world or new data to make decisions or forecasts. So why it matters? Prediction is the final goal of most machine learning systems, that is turning input data into actionable insights, and accurate predictions support tasks like product recommendation, we have fraud detections, we have medical diagnosis, and more. So we have some real world deployment of model depends on reliable prediction performance. And now we can finalize our model. The model.fit will have to pass on the text, comma, labels, and prediction will be equal to model.predict, and we say we want to predict I enjoy AI research if it is either positive or negative, and we print prediction and we pass on the prediction parameters. Now let us head to VS Code and run our stuff. Here in VS Code, these are our codes. So let me run pyml.py, and if I hit enter, it will take some time to analyze. And voila, you can see the classification, text classification. I love coding. This is a positive statement. Debugging is so hard. It's a negative statement. And addition prediction, for example, I enjoy AI research. So this one was a wrong classification. And you see, I enjoy AI research. This should be a positive stuff. So we need to know how to play around with your models, so to make sure that the accuracy is as per. Now guys, next is that we're going to look at reinforcement learning. So let me give you a gist of what we want to look at. So we want to understand what's reinforcement learning, or RL. So can you see my screen? This is an example of reinforcement learning. So we want to produce something like this. So this is the stuff we want to produce at the end of our code. So before we produce something like this, we need to have some history about reinforcement learning, some examples like this. So please observe this image well, because this is what we are going to use, and we are going to code from start to finish without displaying. So you can guess what this is trying to do. So it's like a vertical, it's like a stick trying to remain vertical along that line. So it's like being forced to make sure that it remains along that line without deviating from the setup rules. So I hope this will make sense. So let me proceed to my coding interface. Now guys, let us head on part 3 on reinforcement learning, or RL. And remember, RL, or reinforcement learning, involves training agents to make sequences of decisions by rewarding desirable behaviors. And key components include agent. In this case, when you refer to agent, it's the learner or decision maker, and environment as well, the world agent interacts with, and the reward, or that is the feedback signal. And let us import some modules to use in this project. We need to import gym or GYM, we need to import NumPy as NP, we need to import matplotlib.pyplot as PLT, and in the following section we want to create the catpole environment that we will just see with render mode specified. So remember, catpole, for those who don't know, is a popular reinforcement learning environment provided by OpenAI's Gym, used to demonstrate and experiment with reinforcement learning algorithms. And the problem that we want to solve is the catpole problem. Involves a cat on a track that is tasked with balancing a pole on top of it, the way you just saw, and the goal is to keep the pole upright for as long as possible by applying forces to the cat. And the details of the environment are as follows. The state space. The environment provides a dimensional state space, which includes cat position, and this is the position of the cat on the track, and also we see the cat velocity, the speed at which the cat is moving along the track, and the pole angle, the angle of the pole with respect to vertical, i.e. how tilted the pole is. And we can also see that the pole angle velocity, the rate at which the pole is rotating. And now action space, there are two possible actions in cat pole. One is 0, which indicates push the cat to the left, and one push the cat to the right. And goal of these actions is that the goal of the agent is to keep the pole upright for as long as it is possible. So and the agent must balance the pole by moving the cat left or right, and the episode ends if the pole tilts past a certain angle, usually 15 degrees, and the cat moves too far off the track beyond plus or minus 2.4 units, and a predefined number of time steps, that's usually 200, is reachable. And rewards entail the agent receives a reward for each time step the pole remains balanced, and typically the agent receives a reward of +1 for each time step it succeeds in keeping the pole upright. And cat pole use in reinforcement learning follows. So the cat pole environment is often used as a benchmark problem for reinforcement learning algorithms, as it provides a relative simple but challenging environment to test the agent's learning capabilities, and it is a classic control problem where the agent learns to control a system based on feedback, the state and reward. An example task for agent. So imagine you are the agent. You are controlling a cat on a track. A pole is attached to the cat via a hinge, and the pole is initially upright, but you must move the cat left or right to prevent the pole from falling over. Why cat is popular? It is simple yet challenging. It is simple enough for people new to reinforcement learning, but also challenging enough to evaluate different algorithms, and it is continuous action. So even though the actions are discrete, that's left or right, the state space is continuous with real valued numbers for position, velocity, and angle, which requires the agent to learn from continuous feedback. And educational now, it is used in many reinforcement learning tutorials to explain key concepts like pure learning, policy gradient methods, and value-based learning. And let us have our example with an object E for environment gym.make catpole 1, renter mode will be human, and in a number of action is equal to in.action underscore space.n, which will be the number of possible actions. So let us discretize the continuous state space into bins. A state underscore bins is equal to a list of np.line-space negative 4.8, 4.8, and 10. So this in this cat pole or the cat position, and np.line-space negative 5, 5, 10. This one, it is the cat velocity, and np.line-space negative 4.18, 0.41810. This one will entail the pole angle. np.line-space minus 5, 5, 10. This one will depict the pole angular velocity. And we can define a method, discretize underscore state. Now this one we want to pass, or we want to convert to continuous state into a tuple of discrete indices. So we can return a tuple, int np.digitize with s and bins functions, and for s bins in zip state bins. Now we need to do what? To initialize the q table. Q will be equal to np.zeros 10, 10, 10, 10, n actions. And now let us understand what is hyperparameters in this case. Hyperparameters in machine learning are configuration settings defined before training. But remember, the next step is we want to define our hyperparameters before training a model. So unlike parameters like weights in natural or neural networks, which are learned from the data, hyperparameters are set manually and control the learning process. And examples of hyperparameters include learning rate, how much the model adjusts in response to the error each time it updates. Too high, that is too high is equal to unstable. Too low, it can be slow learning, and among other stuff. And also, you can also look at the number of epochs. So at this moment, we know we understand epoch. What's epoch? How many times the model sees the entire training data set. Previous model we use like 20 epochs, so like 20 times, and batch size we use mostly 64. And this is the number of training samples used in one iteration before updating the model itself. And now we can also look at the number of layers or neurons, and this one is then in neural networks. This defines the architecture, and we can look again under hyperparameters. We can also look at max depth for decision trees. It limits how deep the tree can grow. And regularization strength. This one helps prevent overfitting by penalizing complexity such as line L1/L2 regularization and k in k nearest neighbors, which means that the number of neighbors to consider when classifying a new point, and why hyperparameters matter. They greatly influence the model's performance and training time. Again, proper tuning can help prevent overfitting or underfitting of models, and so selecting the right hyperparameters often involves techniques like grid search, random search, or Bayesian optimization. And you can think of a hyperparameter like the setting on an oven. They don't change while baking, but choosing the right temperature and time is crucial for a good result. So let us proceed with our hyperparameters. Alpha will be 0.1, that's which will be our learning rate, and gamma will be 0.099, which will be the discount factor, and epsilon will be 0.1, which is exploration rate, and episodes will be 1,000. And you can store the rewards for plotting. So rewards will be an empty list, and training, let us create a training loop. So for episode in range episodes, so 1,000 episodes that we're expecting. State is equal to done is equal to false. Total will be underscore reward will be 0, and while not done, epsilon greedy this epsilon greedy action selection function. So if np.random is less than epsilon, then action will be equals to n for environment dot action underscore space dot sample. So we want to explore. Else, what else? If we don't want to explore, action will be np dot argmax with q and state. So which means we want to exploit the best action. And next option or next observation, reward done underscore comma underscore is equal to n dot step action, and next underscore state is equal to discretize underscore state next obs, and hashtag q learning update, which means you want to update the q learning state, and q state action will be an increment of alpha times reward plus gamma times np.max q next state minus q state action. So state will take the value of next state, and the total reward will be the addition of the reward, and rewards will be rewards that append to total rewards. Now we can print q learning training complete to figure out what our output is. So let us look at the plotting now. We want to plot now our stuff. So we need to plot total rewards over episodes. So plt.plot, we pass on the rewards. plt.title, total rewards over epsilon. So episodes, and plt.xlabel will be episodes. plt.ylabel will be total rewards. And plt.grid, which is true. plt.show, again to display the image or the picture or the image that will be produced. Now this is what will appear. Watch the trained agent perform. This is what will appear at the top of our agent as will be working, or the way you just saw him. You can say him or her. So we can print watching trained agent. and say choose the window to exit. State is equal to discretize underscore state and dot reset 0. Done is equal to false. While not done, then env dot render and action will be equal to np dot argmax q state and obs underscore comma done underscore comma underscore is equal to env dot step action. Then state is equal to discretize underscore state obs and env dot close. So we need to close our stuff now. Now let me head to VS Code again and run our. So this is our project again. So let me run py mlai.py or machine learning and artificial intelligence. If I run, it will take some time to process, and we realize that as our agent is working, and you see the way the agent works, it's making sure that the pole remains straight, moves left and right, but remains along that line without falling. So our program is working, and Pygame, this is a Pygame window. Hello guys, in part 4 we are going to look at our computer vision with OpenCV as our part 4 project on advanced machine learning and artificial intelligence. So computer vision enables machines to interpret visual data from the world, and common tasks will entail common classification, object detection, and image segmentation. So let me give you an overview of what we're expecting at the end. mlai.py, and if I run, let me expand my terminal. I check the output that will be associated. So can you see all these people who have this image face detection project? The image, you have 5 individuals, and the program is going to identify how many people are in this image, and the image can be first of all, after detection, image can also be converted to a grayscale. So remember, it featured everyone's face uniquely. So and it reminded us that we have 5 individuals on these images, and if you provide the image with one person, it will tell you that we have detected only one person or one face, and the same image was converted to grayscale. Now we can detect the age detection, so we can detect each age of an image. So can you imagine how this image looks? All the ages are just extracted from here, and this is the power of OpenCV library, or in this case we say CV2 library. So I hope guys are going to enjoy as we proceed in a pragmatic session. So guys, this is the image, this is the original image that we are going to work on. So stay put as we move to our coding section. So this is the image in fact that we're going to look at it, how it's going to be highlighted each face uniquely, and now we count the number of faces that were detected. Now guys, let us proceed on part 4 of our project, computer vision with OpenCV. I hope you enjoyed this. So our computer vision enables machines to interpret visual data from the world, and the common tasks include image classification, object detection, image segmentation, and we can install unnecessary packages, or if we want to install OpenCV, we need to use pip install OpenCV -Python. And let us define our project. So def computer underscore vision underscore example colon, we need to import CV library from OpenCV library for computer vision tasks. I also need to import NumPy as NP, that is for handling arrays. So remember, NumPy is very powerful library. It almost is used in every purpose. So, and you also need to import matplotlib.pyplot as PLT. So matplotlib is used for plotting purposes or displaying images. We also need to import OS for which OS module to work with files and file path. And again, we need to load now our image. Remember, we image I have just shown you, and I named this group of people.png, which will be the path to our image. Now, the file. So, if not os.path exists, image path, which means to check if the image file exists in our working directory, and we need to print the image file and pass on the path not found. So the provided path was not found, and we print now error if the image is missing. Now we need to again to return, which means we want to exit the function, and now we need to proceed. Image will be equal to cv2.imread and pass the image part, which means we load the available image using OpenCV library. And if image is none, we check if the image was successfully loaded. Now we need to print failed to load the image. We need to print the error if the loading failed, and we need now to return, or we need to exit the function again. And now let us convert the image to grayscale as you saw it in the second partition. So grayscale or gray is equal to cv2 cv2 color with image and cv2 color underscore bgr to gray, which means to convert the image to grayscale. And we can also do face detection the way you saw at the far end where all faces were detected, and edges will be cv2.canny and gray 100 by 200, which will detect the edges using the canny algorithm function. And now we can have a face detection method, face underscore detection object. Our cascade method will be cv2.cascade classifier, which means we are loading the pre-trained face detector, and cv2.data.her cascade plus her cascade underscore frontal face underscore default.xml, which this is an XML file for face detection. And faces will be equal to face underscore cascade dot detect multiscale, which means we want to detect the faces in the grayscale image, and gray comma scale factor will be 1 to 1, and mean neighbors will be 5 with parameters. That is the parameters to control the detection accuracy. And you can print faces detected will be the length and because of the number of faces, and which means you are printing how many people or how many number of faces were found during that execution. And for x, y, w, h in faces, so we need to look through each detected face. cv2.rectangle with image and x, y, x plus w, y plus h 255,002. So we need to draw a blue rectangle around each face, the way you just saw the first image. Now we need to show all the results using matplotlib. So plt.figure, we want to set the image or the picture size or the figure size specification with 15 by 5 inches, and original image with face detection follows. So plt dot subplot 1 by 3 by 1, so which means it will be 3 images in 3 columns or in 1 row. So first subplot in 1 row 3 column grid. So plt.im show cv2.cvt color image and cv2 color underscore brg to rgb, which means we are converting brg to rgb, and show the image. And plt.title, you can say face detection, the title for the first image. And plt.axis, you can set the axis off, which means we are hiding the axis text, and grayscale image. So plt dot subplot comma 3 by 2, which means we are creating a second subplot. Plt dot im show gray, and map will be gray, which means we want to show the grayscale version of the provided image path. And plt dot title will be grayscale. This will be the title for the second image. And plt dot axis off, and we want to hide the axis ticks again. Edge. Now the final stuff, we're going to look at edge detection, the third image that we saw. At plt dot subplot 133, that is the third subplot. So plt dot im show edges, map will be gray, and we want to show the edges of the detected edges that were detected. Plt dot title will be edge detection scanning, and title for this will be the title for the third image. Plt dot axis, again we're setting all axis to be off, we're hiding the axis ticks. And plt dot type layout, which means we want to adjust the spacing between the plots. And plt dot show, we want to display the image back to the user. That's all the images, and we can now call the function to run the code above. So computer underscore vision underscore example and bracket, then which means we are executing the function. And now if we run, you get what the program showed us earlier. So let me run. So this is our program. If I run by ml.ai.py and I hit enter, this is our final output. From the terminal, you realize that we have 5 faces detected. 5 faces detected. If we revisit our image or our output, you realize indeed there are 5 people or 5 faces. 1, 2, 3, 4, 5, and we have grayscale and edge detection. This is amazing. This is the module summary. That is module number 12. And the key takeaways that we learned today is deep learning. And we looked at TensorFlow, which is high-level keras API for quick prototyping. And we also looked at PyTorch, which is flexible, research-friendly framework. And also looked at number 2, natural language processing, which entailed text pre-processing, tokenization, stemming, among others. It also entailed text classification using machine learning. We also looked at reinforcement learning, which was we looked at Q-learning algorithm. Also looked at balanced exploration versus exploitation. And number 4, computer vision, which is our last project, which entails image processing fundamentals, object detection with her cascades, and the following are practical applications that you can proceed to do further research. Building your own intelligent chatbots using NLP, developing self-learning game APIs using reinforcement learning, creating image recognition systems using OpenCV, and implementing recommendation systems using deep learning. I wish all the best, guys, and remember, I'm going to provide these codes or these source codes via my GitHub repo. So don't worry, I will attach everything. So see you in next module, and please subscribe to my channel, like and share and comment to support my work. Thank you.